So in this slides, what we will do is like we do the 2D rotation of the point. So what we already know is the location of the P, and also we know the angle between this line and the x-axis, which is alpha, and we know the angle we rotate from P to P prime, so which is just theta. And we also know the location, distance between the origin and the P, point P, which is L. So we need to obtain the location, the location of the P prime, which is the value of the X prime and the Y prime. So actually in here, what we will do is like, we wanna use the variable and the values already know to represent or to obtain, in other words, is obtain the X prime and the Y prime. So in this, we can describe a 2D rotation of the points. So what we will do is first, we will first to convert the x and y, these values, using L and alpha to represent this. So first, we look at the triangle. So there is a triangle here. So you see this blue triangle? In this triangle, we know this angle is theta. And this edge, this boundary is L. So that means x is equal to this length, and the y equal to this length. So now, according to cosine and sine, we will have cosine alpha equal to x over L, and the sine alpha equals to y over L. So based on this, we can get this, right? X equals to L multiplied by cosine alpha, and y equals to L multiplied by sine alpha. So this is the first equations we get. And now we move to the second triangle. Okay, the second one is go from the origin to the P prime, this triangle. So in this triangle, this length is x prime, and this length is y prime. So this angle is theta plus alpha. Okay, so right now we will have, using the same way, we will have like cosine theta plus alpha equals to L prime equals to L, and sine alpha equals to this. So we can also, based on these two equations, we can get this. Okay, now as we need to use these two, equation 1, equation 2, and to try to use x and y to represent x prime and y prime. So let's remove. It's too small. Can I make it bigger? Okay, anyway. So here, how to do this? First, you need to know an equation that cosine alpha equals to theta equals to cosine alpha cosine theta minus sine alpha sine theta. And another you need to know is sine alpha plus theta equals to cosine alpha sine theta plus sine alpha cosine theta. So this is just the mathematics. So I believe you learned before. So times L, both the left and the right side, you will get this. And these two equations is exactly the same as this one. These two. So that means after we can split it up, it can alpha and theta, we can have these two equations. So look at these two equations. You will find L cosine alpha is equal to x, and L sine alpha is equal to y, right? L cosine alpha equal to x, L sine alpha equals to y, right? So substitute, using x and y, replace this stuff, and then you will get the equation, this equation. Okay, so in these equations, it's just we change the formats, writing using the matrix format, and then the left side will be x and y like this, and the right side will be like this, like this red part. And if you want to validate it, you can every time go into it, right? Go into it, and you will have cosine theta x minus sine theta y, and sine theta x plus cosine theta y, which is equals to this. So we kind of validate it. So we use the matrix formats to show this, right? And we give it a name. Give this matrix a name. We call it a rotation matrix. So after we apply this rotation matrix, we can convert the arranging value, arranging position of P, to get the new location of the P prime. So this is how we do 2D rotation of a point. So in this slides, we want to extend our 2D rotation to 3D dimensional transformation. So our 2D transformation, not 2D rotation. So in here, what we have is we have a translation which is easy to understand. We have a 3-axis, right? X, Y, and Z, X prime, Y prime, and Z prime, and we move from the point P to P prime, right? So because it's a translation, so we just add dx, dy, and dz respectively to x and y and z, and then we will get P prime. So this is easy. And another is rotation. How we do rotation? For example, this is a rotation around z, and this is x, y, z. We, in 3D dimension, so we add another column, kind of another dimension to it, which is independent to the 2D pattern. So this is kind of independent. So if you want to validate it, same thing, you need multiply the x and y and z into the matrix. So after that, what we will get? We will get x cosine and minus y sine theta and plus z times 0, right? Times 0. And we will get x sine theta add y cosine theta add z multiply 0. So for this one, we will 0 x 0 y and 1 times z. So after simplify this, we will get x cosine theta minus y sine theta, x sine theta, y cosine theta, and z. So after rotate, because you rotate around the z, so z should be the same. So you will see the z is the same. And the x and the y, it's just equal to what we have in the 2D rotation. So this is the rotation around z. So same thing for rotation around y and the rotation around the x and the y. So in the exam or just in this calculation, what we you need to remember the equation and put the values into the equations, and then you will get the calculation in 3D stuff, 3D rotationing. So the next part is introduction to the homogeneous transformation. So in the previous slides, we mentioned the two transform, right? One is the translate. Another is rotation, right? So for the translate, we need add another matrix, which is a 3×1. So dx, dy, and dz, right? For the rotation, it's a 3×3. 3×3 matrix. So these two are not are not they're different. So if you want to use the computer to calculate it, you need to tell the computer which rich format or rich matrix we want to use, right? So in order to integrate these two, so for both translation and the rotation, we want to use just the one matrix to do all of them. So we don't need to change the format of the matrix. So integrate these two operations. So we introduce the homogeneous transformation. So what we do is we combine translation, rotation, make the homogeneous version to be 4×4 matrix. And the homogeneous transformation looks like this. So we have 0, 0, 0, 1. Okay, so there is 3×3 rotation matrix, and we have another 3×1 transform. So in here you can see this is the 3×3, and this is the 3×1. Okay, so these two, these two transform. These two, one is rotation, one is transformation. Okay, so in this way we integrate the rotation and the transformation together. And if we want to do translation, we just keep this rotation to be this unit matrix, which is a 1, 1, 1 vertex, and another 0, and we just put the values dx, dy, dz to here. And if we want to do the rotation, only rotation, we just keep it 0, 0, 0, 1, keep the transform to be 0, and put the rotation matrix there. So if you want to validate it, this is the point we have, P, right? And if you want to validate it, you need multiply x, y, and z, and 1 into matrix. So what you will get? You will get in the first column, in the first row, you'll get 1x, right, plus 0y plus 0z, right, plus 1 dx. So what you will get is x plus dx for the first, right? Do the same thing for the second row. You will have y plus dy, z plus dz, and the last is 1. So which is this one? So actually in this way, put this rotation, the to be unit, and put dx, dy, dz to here. What you will get? You will get this. So that means in this way, you can do translation without rotation. You can do translation in this way. And if you want to do rotation, you can just put this as a 0 and put this as rotation. And if you want to validate, you will do the same thing. You can do the same thing to, times the every values x, y, z into the matrix, and you will get the values which are exactly the same to the rotationing matrix what we just introduced previously. So I will not tell more, and we move to the next slides. So next slides, this slide tells you if we have multiple operations, we have a lot of rotations, and we have a lot of the transformations, translations. How we calculate it? So how we do it? For example, we have a1, which is the first point, and after a translate. So this is the translate matrix. So after translate, we'll get a2, which is a new point, right? This is a transformation matrix. So we got a2, and we have another transformation, right, to transfer the point from 2 to 3. So we have a2, so h2, this is h1, let's do h1, h2, a3. Okay, so we can do a lot of these operations. For example, we have a n minus 1 point, go to h n minus 1, go to a, right? So we have n times of operations, transformations. And you can look at it. This is a2. You kind of replace a2 by using hy and ny into it, substitute it. You will get h2, h1, a1, right? Same thing for the n. What you will get? You will get hn, h2, h1, a1, right? So this all stuff is a kind of a combination of the of the transformation matrix. So this is how we do the composition, do the combination of the multiple operations. So what you need to know is like all the operations. So first operations will be at the most right, and then add more operations to the left. So in the calculation, you can calculate this, and after get the new points, and involve this, calculate this, and then involve another, and involve another to calculate. And if you have a MATLAB or laptop, so what actually it's easier, it's like you can calculate all of h, make it the h total, and then calculate h total times a1. So this is another way. It's kind of convenient for the cases that you have a solid, you have multiple points you need to calculate. So after you get this, the only thing you need is just to change this point to a1, a2, a3, a4, and get a prime, a1 prime, a2 prime, a3 prime. So it can save time. So this is how we do the composition of the multiple operations. And this is the examples. This example just to show some compensation examples. So one thing I need to mention here is so here we have the triangle. Oh no, we have a rectangle, right? And in this case, we rotate about point P, but not origin. So one thing I need to mention is all the homogeneous rotation or transformation, translation, they are all rotate or translate based on the origin. Rotate, especially rotate around the origin. So right now, if we do the P, we cannot directly apply the matrix into it. So what we usually do is first we move this P, do the one translation, move the P back to origin, and we will get this, right? This is the first step 1. And the step 2, we use this as the center to rotate. This is a step 2. And after that, we move it back. Do another translation to move it back and to get the final position we want, which is a step 3. So this is also, I believe, some question 4 in your homework. So this is how you treat this kind of stuff. So in this slides, we introduce a concept of a parametric curve, which is a mathematical concept. So coordinates to represent the points and the curve. What we can use the 2 ways. One is we tells you x and y, z for 3 axes. So 3 axes, 3D coordinates. We know every position of x and y and z, and we can describe the curve, right? For example, we have a curve, right? Every point, I give you the x, y, z value. So you know where the point is. Infinity, and a lot of points put together, and it will be a curve, right? So in this way, we use x, y, and z to represent a curve. This is one way. The second way is we use parametric expression. So which is we use another variable t to replace x and y and z, to represent x and y and z. So from the figures, it's we know the start point, and then every time we go really small segments, which we call it delta t, right? And we know another position after we add another plus t, right? So we we know x t1, y t1, z t1, right? This is the first point. And after we move another delta t, we will have x t plus delta t. We also know this one, right? So when the delta t is really, really, really small, that means we repeat at the delta t. We know all these points, right? And then we can use this way to define the curve. So in that way, we can use the expression like this. Using t to represent x and y and z, and we can describe the curves, right? This is another way. We call it a parametric expression. So same thing for the slope. We can also do the parametric expression. So there are two examples tells you how to develop a parametric expression. So first is line, the second is ellipse. Okay, so for the first one, we have an equation expression for the line, which is this one, right? And we just make the x equal to t. We defined, we give it. This is what we give it, and then we can get the y from this. So we use t to replace x here, and we'll have y equals to, at by c equal to 0, right? And we have minus c minus at b to y, and move the negative out, minus out. Okay, we have this. Wait, oh, at, right? At, yeah. So this is this. So in this way, we use a t to represent x and y, to represent x and y, to describe another x and y. Okay, this is the line, and for the ellipse, right? This is the equation for that, and also we know cosine alpha square plus sine alpha square equal to 1. So we used cosine alpha to replace this, use sine alpha to replace this, and then we have x equals to cosine y equals to sine alpha. Yeah. And we manage this equation expression where we have this, and this is have this. So now we use a 2, this is the with the constant, and the variable alpha to describe x and y. So this is how we do the metric expression for the curve. So there are conical curves, different steps, and tells you what's the parametric form and what's the analytic form. Okay. So now we move to curve sections. So in the curve sections, so first the thing you need to know is the continuity. So continuity tells you what the types of the, the curve, how smooth the curve it is. So first, we have a C0, which is a point of continuity. So this means in the center point, the point that connect A and B, the intersection between line A and the line B, this point are kind of a joint. So that means the line A and the line B connect to, or go through this point, connect to through this point. So it's continuous from A to B, just a point. You think about it, just a point. And then we move to the tangent continuity. That means in this center point, the first constraint is like the point, right? The value go through this point, point A and point B, go point. This point from line A and this point from line B, they are the same. So this is the point continuity. Based on the point continuity, we need another tangent continuity, which means the line goes through this point at this point has the same tangent to line B at this point. So you can consider it's a derivative go through this point at the same. And then we have a curvature continuity. You can think about based on the tangent. We have two orders of do another derivative. So we have two orders of the derivative the same. So this is the second one. We also call it curvature continuity. So another stuff is a polynomial curves. So for these curves, that means we want to use, so remember you know the parametric methods, right? To describe the curve, which is x, t, y, t, z, t, right? Rt equal to this. And from 0 to 1. So this is the way we describe using the parametric way to describe the curve. So for each components x, y, and z, we want to use polynomial curves to describe it, which means x equal to tk ak minus 1 tk minus 1 equal to a0 equal to a1t equal to this a0. So we use polynomial curve to represent x. So you just remember, this is a kind of a mathematical way to describe the value. Just remember it. And in this one, we go orders from 0, which is this at actually means t0, the power 0. The order, t0. And in here, in this expression, with the highest order is k. So which this is a k order polynomial curves to describe the value. So in here, in order to keep, we can have a freedom for the second, for the C2 continuity, for the curvature continuity. So what we used is cubic. Cubic means the highest order is 3. So I am gonna. So first you can see this is the cubic description. Cubic curve for x and for y and for z. This is the expression. So recall what we mentioned, that we have 3 types of continuity. First is C0, which is the point, right? Another is C1, which is due one time one order of derivative. The second is due twice derivative, right? So we try to do this for x and y. So first we just do the number, right? So now we have this order. We have T3, T2, T1, and T0, right? We do one time of the derivative. For x as the example, we will have x equals to ax 2ax 3ax2, right? X 3ax 2bx cx, right? So we still have this components, the t inside that. With the changes of the t, we can control x, right? We do the c2, we do another derivative. We have a 6axt bx, right? We still have a t components in it, so we can use t to kind of control the x. That means we can change the x values when the t changes. So that means we have a freedom right now to control the x. So that's the reason why we use a cubic. So after 2 times of the derivative, you still have the freedom to control the values of x, y, and z. That means using these formats, we have enough freedom, right, to describe or to make the curve we describe has the C2 continuity. So that's the reason why we call it, it's kind of, we just mentioned, or we use cubic curve here to describe this x, y, z value. Okay. So this is why we use the cubic curve, and what's the formats of the description. And now we just make it as the metric format. Yeah. And after the metric, we call everyone to be a vector A, B, C, D. And this is another vector. Okay, so yeah, and this is the do one times of derivative. Okay, and then we move to the Hermite curve segment. So Hermite curve segment is a kind of a specific one method of the cubic curve. So we call it the Hermite cubic curve. So the Hermite cubic curve is we use the point end-to-end point, and also the tangent. I mean, the tangent go through this point to define the curve segments, to define the curve. So we have this one, right? And we put this one down. So we have we go from this one. We go from here. We go from which part? This part is easier. So we go from this part. So R is the vector of the point. So and equals to first vector, second vector, third vector, the last one vector equal to right. Go from here. So we have another which is the right. So in order to use Hermite curve, describe any curves, you have to know the values of vector A, B, C, D, right? So right now, what we will do is like we will use this. We'll use the two endpoints and the two tangents at the endpoints to get the values of A, B, C, D. So we use the point at the end. We use the endpoint. So P0, right? This vector should be equals to the right part, which is equal to t equals to 0, right? So we will get the matrix, this matrix equal to t equals to 0. And we put z to 0 and put in, and what we will get? We will get A 0, B 0, C 0, D. So get to D, right? So P1 point P1 equals to that match this metric when the teams equals to 1. So point 0 will be 1, 1, C, right? So equal to A, B, C, D. So we have a second equation. So the third one is T1, right? T1 is dt t equals to 0, right? So we go using this equation, and when t is 0, so we will have a0 and b0, c, d0. So we will have c. So this is the third equation, and the last equation is t1, right, equal to so will be a1 b1 c1 0, which is a b c. So in this way, we have 4 variables, which is a b c d, and we have 4 equations, 1, 2, 3, 4. So 4 independent equations can solve for 4 variables. So in this way, we can get the values a, b, c, d by using these 2 points and 2 tangent to describe this. So we get the, for example, f, a, b, c, d, 2. Oh, sorry, never mind. What I mean is like we have a way we can use the point 0.1 t0 t1 to represent a, b, and c, d. So that means here is the 4 equations, and this is the values we get. So now we have a p0, t0, p1, t1 to describe a, b, and c, and d. Then we do the simplification, and we organize it. It will be like this way. So this is how we use Hermite curves. Use these 4 values, 0.0, 0.1, t0, t1, to describe the curve. And this is the examples. In the examples, give you 2 points, give you 2 tangent, and put this into this one, first one, and then you already have this is always the same for the Hermite. So for Hermite curve, this metric always the same, and put in, and then finally you will get the curve. So this is another one. This is only have have 3, not 3, only 2, right? This is still the 2. So the 2 dimensions. So gives you like the point A and point B also give you the slope. So the slope is also the same. Slope is like, the slope is the similar to give you the vector. So you can convert this to the vector by, if you have an axis, x and y, right? Your slope has 30. This is a 30. And the vectors will be, x will be this long, and y will be this long. Imagine this is 1. This is the scale you have. This is the scale you have. The vector, which is a vector magnitude equal to 1. So this is 1, and this is x, and this is y. So x equals 1 times cosine 30, right? So this is x cosine 30. So this is the x, and the y is 1 sine 30. So which is this one? So this is for this slope, how to convert to a vector. And if you have a different magnitude, to magnification to like 2 or 3, you just make this value to 2 and 3. For example, if there's a 2, it's a cosine equals to 2. So this is how you change the magnification. And this is another example. After you change to the vectors, you just put into the first matrix. This is always the same, and using this to get the final answers. So this is another example. And the second type cubic curve is a Bezier curve segments. So right now we don't want to use tangent. We want to use all points to control. So we use the two endpoint and another control point, and to control the shape of the line. And actually, it's kind of the similar thing, same thing to the Hermite. It can be converted from Hermite. It's like we add another this 2, but the tangent part, we just use this 2 point to represent it. It's like the tangent, which is right, which is 0 equals to this 2 P1 P0 n. So n is the order. So this equation tells you so the tangent go through the first point is the same as this point, the line between the point 0 and point y, they have the same directions. So the tangent go through the point has the same direction of the P0, P1, this line. So this equation just tells you this. They have the same equations. So kind of how we get this, we just use these 2 points to replace the tangent parts. So make all the things, we only have 4 points, but not the tangent components, to simplify the calculation. So this is a Bezier curve. And for the Bezier curve, we do have this. So the same process, how you get this A, B, and C, D values is the same as Hermite. We just use the P1 minus P0 3 times equal to R equals to this, and use this to go into this equation. This is P1 P0 3, and this is another. So using this, go to here, and steal out the equations, and after that, you will get the equations of this. So the expression of this. So it's the same idea, same way to get the values for A, B, and C, and D. And we also manage the formats. We have this type for the Bezier. So you need to know, so for the third order, which is the highest order is 3, so this is always, for the cubic, it's always the same, this metric. And after that, we can get this. So this is another format to get the curve for the Bezier curve. So for the curve, you will find we have this, right? So you change to another format, will be 1 minus t3 equals to P0, right? So we have this, and you will find for each component, we can use another way. We can use this. We can use this to describe. So from I equal to from 0 to 3, we have sigma I equal to 0 to 3, b I 3 t p I. Right? This is the we can have this. Right? We have 4 components. We have 4 components to add to do the sum, right? To do the sum. So we use this way to describe. And for this b, we have the equations. We have this to describe every coefficient for every component, for each component. So it's just this. So this is kind of like, so generalized equation to show the Bezier curve, not only for cubic, for all the others. So if the others is a 3, which is a cubic, this n equal to 3. So that's it. And we give a specific name for this b, for this coefficient. We call it the blending functions. So in the cubic, which is n is 3, we can have a 4 cubic. We have a 4 blending functions. So this is the expression for 4 blending functions. So when we plot it, it's like this. This is the blending functions, how it looks like when we plot it. So this is all for Bezier curve. And this is examples. Example just to give 4 points, right? And you fill in the numbers to the first metric, and this metric is the same for cubic, and this is the same, and then you do the calculation, you get the final values, final expressions. So this examples is we give you 4 control points, so you can get this. You can get the final expression, and after you get the final expression, put these numbers into it 4 times, you will get the 4 points. So which is the 4 points. So like this one, just so this is another way to say it, but it's exactly the same thing to the metric stuff, So the same thing, put this into the first metric, and then put into this metric, and then the rest of them are the same. And then last, you can have the expression with include t, and then after you get that, and you put every numbers into it, and you finally will get the points for every t values. So another is continuity. So because for Bezier curve and the Hermite curve, right now we only think about one as a point, right, at 2 end, and also the tangent at the 2 end for Hermite. And also for Bezier, it's the same thing, right? We have a point and 2 and 3, right? We have a 4 control point. Actually, the point PE equal to T, right? So this is we convert from Hermite. So Bezier and Hermite, we have the same. We only do point continuity, and we do tangent, make a tangent the same, so which is the C1, which is the tangent continuity. So for these two types of curves we define here, they only have the C1 continuity. So this is the slides I want to tell you. And the next is properties of Bezier curves. So Bezier curves, is, for example, we have cubic, right? You remember we have a 4 control point. Cubic n is equals to 3, but we need 4 control points. So for the n, which is the order is n, we need n plus 1 control points to do the n orders of the points, n orders of the Bezier curve. And so first, it's easier to understand, right? So the lines will pass through, the curve will go through the first and the last control points. So this is how we, build this, Bezier curve. Second, tangent of so these two equations just want to tell you. So we have a curve. We have 4 control points. P0, P1, P2, P3. So these two equations just want to tell you the tangent line goes through the point 0 has the same direction with this line, point 0, point 1. They have the same directions. Because of we have different orders, so this is the vectors. So the vectors values is different, so we need a times n in front of it. So actually, this equation just want to tell you at the end point and the start point, the tangent go through this point at the same direction of the lines between the two control points, point 0 and point 1, and point 2 and point 3. So they have the same direction. So this is what it tells you. And another properties, this properties is important for the interpolations. So which is the convex hull properties. So that means we have a 4 control point, right? We have a 4 control point. For example, this is a curve, and we have a 4 control point. So the convex hull, which is the polygon, we connect all the control points. So the lines always will be inside of this polygon we circled through the 4 control point. So this is always in the polygons. This is the convex hull properties. So these properties, you don't need to know much about that. You just need to know we want to apply this curve methods into the interpolation. So it has its unique properties. This is a really good one for that application. So another is disadvantages. So disadvantage first, of course, these 2 control points are out of the curve, right? And the second, which is important, is like we cannot locally modify the points. So you go back to the equation here, right? So every point, every time, for every t, for every t, the x and y and z will have contribution from all the control points. So that means for x, you need to contribute every x values from these points will contribute to this x. So that means you change either one of them. So 0, 1, or 2, or 3 all will affect the final values of x for each t. So that means you change 1 point, you will change the curve, the curve shape. That means you cannot, locally change the curve, right? You change 1 point, you will change the overall shape of this curve because the x has all the contribution from all the points, all the time from t, and at any t moment. So that means you cannot do local control. So in the figures, it's just like this. This is a global modification. you just change one point and all the curve will changes, but not like this is local, we change one point, the first parts are the same, only the local curve will be changes. No. So for this Bezier, it's because the way we build it, the way the structure of the expression of this curve, how we describe this curve, it we cannot locally control it, locally modify it. So this is the third one is like the order. It's related to the number of the control points. So remember, for Kubrick, we have order of 3, right? We need the n plus 1, which is a 4, as the control point. So if we add more control point, we want to add the higher orders. For example, order 4, we need the 5 control points. We want to order k, we need a k plus 1 control points, and then we can achieve k orders, which gives a lot of troubles into the the calculation. If we want a high orders lines, we have added more and more control points and make the orders to be more. So which is a kind of make the calculation more complicated. So this is one of the disadvantages of the Bezier curve. And another is we want to solve one thing. So we want to solve, so first we want to have the orders can be more freedom to control points. So this is the one thing we want to solve, right? Which is the order stuff. So the highest we want a freedom of the highest order of the line to be different from the control points. So this is the first thing we want to solve for the disadvantages, right? The second disadvantages is like we cannot do local control. We cannot do local control of the Bezier, right? So we want to solve these two weaknesses. So we introduce the B-spline. So B-spline is a generalization of the Bezier curve, but it has more advantages compared with the Bezier curve. Like I said, we want to solve these two weaknesses. So first, we need to know the B-spline. So how we build the B-spline, construct the B-spline curve. So these 3 equations help you to construct it. So, but it's kind of hard, just not intuitive here. So I will explain using the cubic, which is easier to understand. So, okay, now and in order to understand this equations, we just take examples, and in these examples we make k equal to 2 and k equal to 2 and n equal to 3. So we substitute k and n into the equation. We have left this one pu equation, and we expand it to see every component. So we have a 4, one is P0, one P11, P2, P3, right? We have 4 components. For each one, we do one by one. First, we do the first components. So we need to know n0 to u. So n0 to u go from to right side. N0 to u from the equation we have a this. It can be this 2. So it consists of 2 parts. One is n01, one is n11. So that means we used n01, n11 to describe n02. So for n01 and the n11 in the slides, it tells you the values, right? So from the u larger between t0 t1, n01 is equal to 1, and otherwise it's 0. Same thing for the n11, when u is between t1 and the t2, n11 is equal to 1, otherwise it's 0. So that means we go down, we have a n02, right? So represent p0. So n02, we need n1, n01, n11 to get n02. For n12, we need n11, n21. For n22, we need n21, n31. For n32, we need n31, n41. And for n01, 1, 2, 1, 3, 1, 4, 1, we already know for n01 is equal to 1 when you between t0 and t1, right? n11 between t1, t2, n21 between t2, t3, n31 between t3, t4, n41 between t4, t5. So in our equation, we have 4 control points. We have n equal to 3 and n plus 1 equal to 4 control points. And we have a k equal to 2. Go back, we find when k equal to 2, we need to make, this n number go back to 1, so once, right? So, and after that, we have, we kind of expand, we create 5, 1, 2, 3, 4, 5 segments. So we need the numbers the segments t0, t1, t1, t2, t2, 3, 3, 4, 4, 5 segments. And using these 5 segments and using the equation involved in the n01, 1, 1, 2, 1, 3, 1, 4, 1 to describe PU. So now we remember we have a 4 control point, n is 3, 4 control points, k equal to 2, we have a 5 segments. We have 6 t numbers from the t0 to t6 to t5. We have 6 t. So remember this. So this is the we constructed this, So we build this PU when k equal to 2, n equal to 3, what we will use and what the numbers involved in these equations. And we go to these equations. We go here. Remember the number is n equal to 3, k equal to 2, and we have a control point, which is a control point is n plus 1 equal to 4 points, control points. Right? We have segments, 5 segments. And we have a 6 t values, right? From t0 to t5. So here, these t values, every t, we call it not values. So this t is not. So we call it not values. And u is the parameter variables help we, using these equations help we is kind of we define one. And another variables help us to do the calculation. So these numbers you remember it, and then we move to the next step. So next step is knock values. So knock values, you can see how many knock values we need to have. In our examples, we have n equal to 3, k equal to 2, and we have 6 t values from t0 to t5, right? We have 6. So go back to here, we find n plus k plus 1 equal to 3 minus another 2, another 1, 6. So this equation, or this k plus n plus k plus 1, it comes from what we have, right? What we have, go back to here. So go back to here. This tells you why these numbers the knock numbers is come from n plus k plus 1 is because during the process we can validate, or we can tell you where this is come from, okay. And the next part you need to know for the t, so we only know we need 6 t values, right, from t0 to t5. Then what values are they, exactly values are they? So there are two types of knots. So one, it's called a periodic knot, means the interval between knots are the same. Okay, this is the first periodic knots. The second we call the non-periodic knots, which is we repeat several times at the beginning and repeat several times at the end. So the intervals between the knots are different because we repeat first several times, right? That's the interval is 0. And at the last, in the end, we repeat another several times, which is 0. But in the center, there is a certain interval. So the intervals in the whole range is different. It's different. So that's what we call non-periodic knots. So for example, in our case, we have n equal to 3, k equal to 2, right? Yes. And you will see I will be 5. Smaller than 5, larger than 0. So t0 will be 0 minus 2 minus 2. So will be negative 2. T1 will be negative 1, right? Until T5, it will be 5, 3. So the T numbers from 0 to 5, if we use periodic, in our case, it will be this. And if we choose non-periodic knots, we will have what? So I is minor than 2. So from 0 to 2. So that means T0 equals to T1 equals to T2 equals to 0 in our case. And when the I is larger than n is 3, right? So I is higher than 3 but smaller than 5 in our case, right? Will be the same, which is 3 minus 2 plus 2 equals to 3. So that will be like T4 equals to T5, right, equals to 3. So in the center, it will be I minus k equals to 1 from k is 2 and is 3, right? So we will be I 2 and 3 will be Ti equals to I minus 2 plus 1, right? Equals minus 1. So T2 will be 1, T3 will be 2. So to summary, like the whole knots values from 0 to 6 will T0 to C6 will be 0, 0, 0, 1, it's from the 2, 2, 2, 3, 2, 3, 2, 3, 3. So this is the final for the non-periodic knots. So what's the difference between the in the actual control, the periodic nodes and the non-periodic nodes, it's will be like this. So we have let's do another. So for example, we have a curve, and in our case, n equal to 3, k equal to 2, and we have a control point of 4, right? Control point of 4, and minus 1 control point will be 4. So the control point will be like this. So for the oh oops for the this is the periodic. So for the periodic, the control point will be like this. So this is the P0, P1, P2, P3. So you will see, because we have a T start from -2, right? And the end of 3. So the start point and end point of the control point will not on the curve, because T is -2, T is equals to 3. Go back to the equation. The P0, P1, P2, P3 are all not on the curve. So this is this is periodic, but for the non-periodic, it will be like this. So the start point and end point of the control point are on the curve at the end or start of the curve. So this is a non-periodic. Unperiodic version. So in the actually in the CAD in our software, non-periodic will be used mostly. Okay. We have a T I 0. Okay, based on these equations, we can calculate it. So n equal to 3, and k is 3, n is 2. So we will have I smaller than 3, larger than 0 will be 0. So which means T0 equal to T1 equal to T2 equal to 0, right? And we have a n equal to 2, 5. So that means T3 equals to T4 equals to T5 equal to 1. And go back to the equation. You have a 0, 3, 1, 3, 2, 3, and you need to use Ni2 to represent this. You need Ni1 to represent this, right? And then just calculate to step by step from you using that equations for the B spline, to use I2 to represent, or Ni3, and to use the components of Ni1 to represent I2, and to get the final values. And it's a really long calculation, so I will not just show here. But anyway, one thing you need to know for the B-spline curve. B-spline curve is when the k equals to n plus 1. So Bezier is the specific case. I mean some special case of a B-spline curve. So go to the property of the B-spline. we know, right? In the cases we talk about, so we have a n, which is the control, no, which is the order, and the n plus 1 will be the control point. So n equal to 3, we have a 4 control points, right? So n plus 1 will be control points numbers. And how many control points, we will have how many components in the equation, right? When the equation, there will be I equal to 0 and pi plus something, right? Plus something. So I'm at times something. So if we have n and we have a p0 to pn, so will be n plus 1 control point. So for this, every control point has a function of a blending function here. So that means we have a n plus 1 blending functions too. And knock values. So because we need to make 0, 3, or the high order of n values of n, which is the blending functions. No, not blending function. I'm sorry. The n values. So n values, you need to make the high orders n values to be represented by the lower orders of n, right? And every n you need to make its lower orders of a 0 to represent the order of 2, right? You need the order of 1 to present to calculate. You need 1 to calculate 2, you need 2 to calculate 3. So for n0k, nik, for k levels, k orders, so you need to use k minus 1 until, and repeats until 1, the order of 1 to describe it. So in this case, we need more, the knock values, which is a t in the examples, right? We have a k equal to 2, n equal to 3. We have a 6 t's. 60 numbers. So go back to n plus k plus 1. This is the calculate the t, how many t's you have. So it's n plus k plus 1. And you need to know, for this ik stuff, we have a degree of the k minus 1 and the order of k. So that means the order of the line is not related to the control point. We can define separately, use k to define the freedom. The degree and the order of the line, of the B-spline. So this is how we solve the problems for Bezier, right? And also, you can go back and see the functions here as the example we have here. So for the point P, right? If it's k equal to 2, point P only control the segments 1, right? Segments 2, only control these 2 segments. That means if we change the values of P0, only these 2 segments will be affected. So the rest of them, like the 3, 4, 5, will be the same. So the value will be the same. So that means if you change the P0, P values, you will not affect the whole curve, but you just affect some of them, which is based on this, which means we have the abilities to do the local control, because we change one or change several control points will not affect the whole curves, but just affects some area. This is another, the weakness of the Bezier line, and we solve it using this way. So right now we solve the way we know we have a separate orders of the line of the freedom, which is k, and we have we have a local controllability to this curve. And the value of the k is called the order of the B-spline. So that is the B-spline stuff. And this is the examples tells you how to calculate for control points and segments of curves. So for example here, n we have a 5, so we have a 6 control points from P0 P5, and we need the order of 3, right? So what we need is and this is the examples tells you how to calculate the control point, how to calculate the segments of the curves. So in the examples, we talk about like, so the n equal to 3. Oh, okay. N equal to 3, and the n equal to 3, and the k equal to 2, right? This is in our examples. We know we need 6 t's from t to 5, right? We have 5 segments. So we have a segment t0 to t1, t1 to t2, t2 to t3, t3 to t4, t4 to t5, which is 5, right? This is how we do that. So this is the segment, the t values, it will be nk1, right? And the segments will be nk. So this is for the when the knots are the periodic. Okay, for the periodic, every t's has the same every segment has the same intervals, and every t numbers are different. So this is for the periodic, but non-periodic will be mostly used in the CAD. So for the non-periodic, how we calculate for the segments, because we have a repeat, we have the same values of a t for several times, right, at the beginning, and repeat these t values at the end. So these examples just tells you how to calculate for that. So for example, n equal to 5, k equal to 3. So the knock values will be this. And the control point is still will be n minus 1, which is 6. So we have a 6 control point from point 0 to 0.5. Right? From the point 0 to 0.5. But the segments of curves, we cannot use n plus k anymore, is because we have a repeat t numbers, t values. So see, first 3 are the same. First last 4 are the same. So actually, how many different t numbers, t values we have? We have a 0, we have a 1, we have a 2, we have a 3, we have a 4, right? So actually, the segments here will be 0 to 1, 1 to 2, 2 to 3, 3 to 4. So this is the actual segments we have. So these numbers will be 4. So if you have it's non-periodic, n minus k equal to plus 2 will be the equations to calculate the actual segments of the curves. And the next thing I need to explain is the important properties of a B-spline. So B-spline has the curve segments for non-periodic will have n minus 2, n minus k equals to and 2, add another 2. So this will be the curve segments numbers for the non-periodic B-spline. And for derivative ups, So for the k orders of k, we will have a k minus 2 continuous cross curve segments. And for the each curve segment, we will it's only affected by the k control points. So for example, in our case, k equal to 2, right? So you only have ni2, right? So for each point, it will affect only, for example, if it's p0, right? It's n02. It's n02 in back to our case. So back to this case. So for p0, it's k equal to 2, p0, we only affect segment 1, segment 2. So that means we only affect 2 segments. So if we increase the k to higher values, we will still have this conclusion that the each curve segment only affects by k control points, and one control point is only affects k curve segments. So that is the how B-spline, we use this type of way to make it localized, and use k to define the orders, and use the k to control how many curve segments and we will affect, and one curve segments by affected by how many control points. So this is the important properties of B-spline. It's different from the Bezier and Hermite curve. Okay, so that's all.